Okay, so maybe Marcus, you could start sharing your screen. And
yes.
Get started.
Okay, so I did share my files now. Do you see the PDF with the slides?
Yeah, it's good.
Okay, great. Should we wait a couple of minutes or just tell me when we're ready?
Wait in maybe 10 seconds. Okay, so good morning, everybody. This is session 23 of the IAEE online conference. This is about investment in electricity. And the first speaker is Markus Eigruber. So you have 20 minutes, so please go ahead. I'll give you a warning with 2 minutes to go if you want. That's okay.
Okay, that's great.
Okay, so go ahead.
Okay, thank you. Okay, great. So this is this presentation is based on a very recent working paper of a colleague of mine, Matthias, Ondra, me, and also Walter Schwaiger. We are all from the Vienna University of Technology in the center of Vienna. And the title is Direct Investments in Renewable Energy Portfolio, Stochastic NPV-based Capacity Budgeting. So the main idea behind this paper is that we're looking at an individual risk-neutral investor who aims at investing in renewable energy technologies, right? Mostly wind and solar. Both, we know, they're intermittent and therefore stochastic in terms of the power output, but also in terms of the energy prices at the exchanges, right? So what we want to do is determine the optimal level of investment in a non-deterministic environment based on a purely data-driven approach, right? This is important to note here. Of course, modern portfolio theory starting with Markowitz in the 50s, the literature based on modern portfolio theory is huge, of course, where one classically at least determines the optimal portfolio of assets based on returns and variance, right? And we do quite a similar thing here. We're working with the minimum exceedance probability framework here. The framework that I will introduce is linked to modern portfolio theory. Some results carry over and some results from our framework can also be used to determine thresholds for modern portfolio theory. So this is basically the outline of the presentation today. The outline here closely follows the sections in the working papers as well. We are firstly constructing the model. We are then calibrating it. So we're using real world data here from an airport here in Vienna, right close to Vienna. We're then solving the model we're using for the sampling approach and also for a constraint discard approach. We're using results mainly from the work of Calafiore. And in the end, I will also present some first validation of the model that we at least up to this point came up with, right? And again, it is important to note that we are basically employing a purely data-driven approach, so we do not assume any parameters on distributions of random variables. For instance, we are just plugging in the data on wind speed and on solar irradiance. For instance, we're transforming them, we're generating output data, and then we're matching this with the prices at the exchange, right? So this is basically the overview. So how does the model look like, right? So we are in the context of optimal portfolio choices in energy economics, of course. We will determine the optimal size of installed capacities. We are looking at solar and wind. So in the use case, we are determining the to be installed capacities of solar and wind energy. And these form the costs of the investments. And these costs need to be minimized, right? Given, and this is the main crux of this working paper, given probabilistic or a set of probabilistic constraints, right? This is the minimum exceedance probability framework. Here at the bottom, the investor imposes a certain net present value that he or she needs to meet with a pre-specified probability. Yeah. And the probabilistic constraint models, they are also quite old, starting in the 50s. And there is also quite an extensive literature already on optimization in this framework and on existence and feasibility results as well, right? So this is why we speak of probabilistic constraints, right? Of course, since we're dealing with renewables here, renewables are intermittent, we all know that. So the net present value is also stochastic, right? So this adds on prior work of my colleague in his PhD thesis, Matthias Ondra, which has also recently been published. And the most basic, easiest version of the model you can see here on the left-hand side in this box here. We are basically, as I've explained, we're minimizing the capital expenditures, where Xi is the capacity of technology I, and Ci are the costs per unit of installed capacity, right? This is a very simple linear objective function, and we are minimizing these costs, these investments costs, subject to a set of probabilistic constraints. And this in this set we have the pre-specified probability here, which is given by key. The investor basically says, with a probability of at least key, I want to have a net present value, so a total discounted cash flow, right, revenue minus costs, of at least theta, right? So in words, and also in our use case, this can be explained by a requirement that the net present value needs to be larger or equal to, say, $1 million or euros with a given probability, right? This is where the probabilistic part comes in, right? And so what we can do and what we did is, and what we need to do is actually come up with some numbers for the net present value, which is comprised of revenues minus costs. At the top, what are the revenues? They're basically the spot market prices. We take them from a local Austrian exchange, not from the apex. I'm not sure about the spreads. Maybe some of you is aware of. Usually one takes the spot market prices from Paris, but we took them here from an Austrian exchange. We have the power, which is being generated by the capacity, and then obviously price times the power is the revenue, and we're also discounting. We're looking at the time frame of 25 years, right? So the energy park needs to be present, needs to be existing for 25 years. This is the planning horizon of the investor, and we're discounting at the rate of 3% annually. Right? And we do take local data, which we plug into these constraints, right? And more on that in a couple of minutes, right? So we take hourly data. We take hourly data from, here it is already. We do take hourly data from the airport, Wien-Schwaiger, which is the main airport next to Vienna, basically. Why do we do that? Because they do have very high quality data on wind speeds, basically. And there's also solar irradiance data at SAMS, which is publicly available, and this, we also use in order to generate power, right? To generate the power that we need to plug into the model. Now for the investment costs, I'm not 100% sure, but this is what we work with here. Wind and solar, we are basically assuming that the capital costs for a kilowatt of installed capacity for wind is 2,000 euro, and for solar it's 800 euro. Obviously, these prices, they vary a lot. Also in the short term, they're constantly, in the long run, they're constantly decreasing. So These are at least the values that we worked with here. If some of you is aware of any numbers that maybe closer matches the investment cost, at least in Central Europe, where we applied the model, then please just let me know. Right. So now we have the data, right? We have the data of wind speeds. What do? We transform them into the power generated, right? And we take some very straightforward transformation functions, right? For wind speed, we have the cut-in speed, the cut-off speed. So if the wind blows very little, right, the rotors cannot be generated and the turbine does not produce anything. If the speed is, if the wind speed is dangerously high, obviously the wind turbine can also not operate. And in between, there's approximately a linear relation of wind speed and power generated. And then there's here the maximum rotor speed, which is safely possible, right? And the picture is even simpler for solar panels because we have the solar irradiance, basically the power of the sun, which is shining on this part in Central Europe next to Vienna, and we are basically transforming them linearly, right? So the higher the irradiance levels, the more power is being generated. Again, of course, for given approximately at least for given efficiency level of the panel. Right? This is what the data looks like here on the left-hand side. We have wind. We have obviously quite a large mass here at 0. This is basically the capacity factor, right? We have a large mass here at 0, so this is where the wind does not blow sufficiently, and we also have quite a large mass here at 1, where the turbine and the rotors operate at maximum speed, and in between we have almost a linearly decreasing relationship. For solar, it looks obviously it looks a little bit different. It's like exponentially decreasing. I think this is very straightforward. And for energy prices, we basically just sample from the local exchange here in Vienna, the EXA, the spot market prices for electricity. And we sample this data hourly, right? So we're dealing with quite a large sample here. We are constructing a virtual with a scenario approach. We are constructing a time frame of 25 years, right? Which is quite a large time frame, but from an investor's point of view, quite a realistic one. We are using a very particular sampling approach, namely that of Calafiori and Campi, and we are basically, so we do have the data hourly. We do have it. We randomly sample from each month 3 days. We do this 10 times for each month, such that we have a month. We do this 12 times so that we have a year, and then we are repeating this process 25 times until we have basically the sample generated for 25 years, right? And we do this because a block size of, like, say, a day is too small in order to capture also here short-term and also longer-term weather trends and effects, right? Because due to the intermittency and due to also in the very, very short-term drastically changing weather conditions, the power output varies as well, right? So this is what the data looks like when we aggregate them. You can see here on the left-hand side, I mean, they are approximately normally distributed on the left-hand side for wind, on the right-hand side for solar. This is basically once we aggregate them over the whole 25 years, right? And so this is basically the input that we use into our optimization problem, right? So what we then do is we after gathering and after preparing the sample, we plug them into the constraints, right? We plug them into the constraints. We are dealing with quite a lot of constraints here. They are probabilistic. So in the general model, we are dealing with 1,002 constraints. Of course, we also have non-negativity constraints on the capacities where the costs need to be minimized, right? And we do generate or take the spot market prices for electricity and the production being generated from our sample, right? And what is nice is that Campi, and also this time with Karate, was able to show that in this framework, if the sample is approximated with this scenario method, that we can discard, so we can omit a couple of constraints and still obtain a robustly feasible solution, right? And the certain number of omittable constraints is given in their paper and also in our paper. It's not that important right now, but and obviously this number depends on the parameters that we impose. But in the end, we were able to discard a couple hundred constraints and still come up with a feasible and robust solution, which is at least computationally speaking very advantageous. Right? So this is the general model here in its basic applied form here. This is the very first use case where we applied these ideas, where we have two renewable energy technologies, wind and solar. We are minimizing the capital costs of investment for these two technologies. And then we have these probabilistic constraints here. Big N, capital N is here 1,000. So we have 1,002 constraints. But again, as I've noted before, we can omit a lot of them in order to still come up with a good solution, right? So what does the model actually plug? What does it put out? Here on the left-hand side, I've put two plots on the left-hand side. Again, we're looking at so the confidence parameter that the investor imposes on the net present value is critical to the ideas behind this framework, right? So we are on the left-hand side, what we do is we plot for each confidence level here. So there's an interval from 0 to 1 because it's a probability. We are plotting the necessary level of investment in order to achieve the threshold of the NPV that the investor imposes, right? And we have used here a threshold in this use case of 1 million euros, right? With of course, with discounting over the 25-year period. So, and at least what you can see here is that the model, this first application, at least it makes sense economically speaking. So once we increase the confidence parameter to the right, so once we basically require a more and more certain outcome, the costs increase, right? And at the end, if the investor requires a almost sure outcome, then the costs they increase convex, or they basically explode, right? And this at least makes economic sense, right? On the right-hand side, we did plot a validation, so that we resampled basically from our data set. We applied the model, and then afterwards we checked whether what the model actually compared to the true parameter came up with. So you can see here at the top these small red, these are box plots, these small red signs here with distributions. So in the end, these box plots, they are always above the 45-degree line, which is the true parameter, right? So in this case, let's take an example here. Say the investor imposes a confidence parameter of 50%, and we are roughly here. And the algorithm that we use to discard is conservative. Let's put it like that, is conservative. The solutions that the model puts out are above this 50% probability, right? This means that
2 minutes.
2 minutes. Okay, I will hurry up. So this means that the solutions, they are indeed valid, right? But what you can also see here is that there's a distance to the 45-degree line. So the algorithm that we use in order to discard the constraints is not the most efficient or the optimal one. It's a heuristic that we use, which puts out nice results, which puts out valid results, right, in this first application. But there's still room to improve, and of course, the efficiency can be improved here. So if I only have two minutes left, so I will skip this part here and jump right to the conclusions of what, I mean, you can do many things with this framework. You can also impose a budget constraint, and then work with a budget constraint in contrast to the ideas that are explained before. Then we can speak also if we compute the inverse probability of failure, basically, right? So it's very easy to do technically to transform this model in such a way. So this is so what I've presented here are the results of a very recent working paper. We have applied this now to again, as I've said, to the use case in Schwaiger in Vienna, with the local data here. We are obviously trying to improve the model to make also the algorithm more efficient, and to also find use cases where we can apply this model and maybe generate interesting insights. So this is a research which is still at an early stage, I would say, and we are of course open and ready for criticism and for ideas on how we can improve the model maybe further, right? And yeah, with that, I want to thank you, Afzal. I think I've spent the 20 minutes that you gave me.
Yeah, right on time.
Right,
Thank you
right
very
on.
much.
Okay.
Thanks, Markus. Yeah, so we have 5 or up to 10 minutes even for questions. So would anybody like to pose some questions?
I'll have a question, Afzal, if I may, Reinhard.
Yeah, go ahead.
Question is, what is the original contribution or contributions of your study? I'm quite aware of the literature in this field on mean variance portfolio optimization for renewable technologies. Is it the probabilistic constraints, or what are the elements that are really novel to your research?
Yes, so the main idea. So if you want to, you can also think of this model like a value at risk model, right? Where we impose a probability and a threshold, but we're looking at gains and not in the domain of losses, like at the value at risk, for instance, right? So the main contribution is to really apply these methods also from Califiore and Campi to an investor because the Califiore Campi methods, they basically they do not at least they do not apply these methods to energy economics. And so this is part of the dissertation of my colleague who studies this problem in his thesis, where he describes the optimal decisions of an investor in a longer term, right, in a 25-year period, renewable energy technologies, right? And the novel thing, I do not think is the model itself, because the model itself is Califiore, Campi, and also Carati, which have been developed elsewhere. But I think the novel thing, or the useful, the goal of this exercise of our team is to apply this to also get some local data, which we did, and then come up maybe with some interesting applications that go beyond what we have initially done here, right? So the main contribution is maybe not present at the moment, right? But we are looking for use cases also locally with our colleagues here in Vienna, where we can apply this framework, right? This is basically also knowledge accumulation of the PhD students as well.
Well, maybe we can come back to this. I have a slide in my presentation with a chronology of this kind of research.
Okay, yes.
The Campi study, I didn't know myself, or I don't know it well, but we can then discuss it maybe again.
Okay, okay, yes.
When it's my turn.
Okay.
All right.
Yes, thank you. Any other questions? Well, maybe I can ask a question. So, Marcus, when you are talking about this probabilistic constraint, and then you say, well, we're actually looking for threshold. So it's sort of like that chance constraint stuff, but not exactly the same. There's also in stochastic programming, people who have CVAR constraints or even CVAR in the objective function. And there's plenty of work in that strand of the literature. So how would you compare your approach to that one? Because that has the flavor of also coming up with investment plans that are somehow robust. I know it's not robust optimization, but somehow they are robust to different kinds of risks.
Yeah, I mean, if you're talking about as I've mentioned before, the idea to value at risk analysis is very very close to the analysis that we do here. And in fact, one can show, if you impose in some distributions and functions, that we have this threshold of theta here, that once we have a solution to the framework of this constraint optimization, we can also say something about the solution of a value at risk, or also a general portfolio optimization technique. So the models or the frameworks are linked. I mean, the main difference is simply that at the value at risk, you're looking maybe at losses, and here we're just looking at the discounted net present value in the future. So we're looking at gains here, right? About the, I'm not, I also must confess, of course, I'm not the expert in stochastic optimization. So I'm not sure if this at least partially answered some of your question about CVARs and about probabilistic constraints in general. I mean, this started, I think, also with Chance and Cooper. Again, the main thing is that we use the Calafiori-Campi approach, and then also the work of Calafiori and Campi, as I've heard here, is the proper pronunciation, to also discard. And also in this approach of Campi, I need to note that we can apply a number of different algorithms in order to get rid of constraints. What we did is we discarded exactly those constraints that were binding in each iterative step. So we remove one constraint in each iteration. We do this a couple hundred times, and we always remove these constraints where the shadow price is positive. This is just one algorithm, and as I've shown here, this is not maybe the best or the most efficient one, maybe a quite conservative one. In the end, it's still a valid solution, but this is also where there's maybe room for improvement and room for developing further ideas on how we can discard constraints while still achieving a more efficient result, I would say.
Right. Okay. Thank you. Are there any further questions? If not, then I think we'll wrap up here and move on to the next speaker. Okay. So thank you again, Marcus. Yeah, thank you.
Stop now.
Yeah. So I guess Jean-Pierre, you're the next speaker, so maybe you can.
Yes, the host has stopped my video. If you want me to share video also.
Yeah, maybe the host can allow you to do that again. I don't know.
Either way, I don't mind. I'm gonna start sharing. Okay, can you see my screen?
Yeah.
The presentation screen. Okay, great.
I'll give you a 2-minute warning, just like.
Okay, great.
So yeah, go ahead.
I'm Jean-Pierre Dib, a second-year PhD in G2E Lab, affiliated to Université Grenoble-Alpes in Grenoble, France. And the subject of this presentation is long-term investments in electrical distribution grids with a real options approach. Of course, the approach is going to be a continuous analytical approach and not a discrete one. Okay, so for the introduction, I split it in three layers. First, we have the problem statement, then we discuss what are real options and what long-term investment we're discussing. So in the context of the United Nations framework on climate change from 1992 and the Paris Agreement, we're looking to actively decarbonize sectors of activity. And as we can see in figure 1, taken from the IAEA CO2 emissions from fuel combustion overview, the largest production of emissions comes from electricity, from the electricity and heat generation sectors, in addition to industry and transport. So efforts to decarbonize these sectors are focused on increasing the electrification of those sectors and reduce fuel combustion when available, which translates in the increase of use and renewable share of production. So the transition has introduced new players and contracts such as demand response contracts or peak shaving contracts. And they redefine the pre-existing relationship between producers and consumers, where we can see the more prosumers introduced to the grid, where they produce and consume at the same time, which affects directly the load power. And de facto, these changes will increase the uncertainty on the distribution grid because the introduction, for example, of renewable distributed energy resources introduces directly weather uncertainties into the load models, which makes control and operational optimization as well as investment optimization much more difficult and subject to continuous change. So facing these difficulties and in an increasingly uncertain context, financial tools currently employed by the DSOs or distribution system operators are inefficient, or they can be very inefficient and do not accurately describe the investment opportunity. Also, the discounted cash flows methods present several unrealistic assumptions, either by removing the inherent flexibility from the decision making or by considering future cash flows as deterministic. So we come, the solution that we present isn't really foreign from literature. It's been applied to transmission system operation or transmission system investments and to also distribution distribution grid investments. But we have concluded that that a real options approach would help us capture this managerial uncertainty and flexibility for and add flexibility in investments for distribution grids. First, what are real options? So real option theory is based on the treatment of financial or investment decision making as financial options, in a sense where the decision maker does not have the obligation, but rather the choice to invest in or mothball or shut down an asset. These options come as an added layer to the discounted cash flows analysis in our case, and are a direct mathematical result of the incorporation of uncertainty in the calculation of expected cash flows. In addition, real options implicitly value future information by altering the timing of the investment, because logically the decision maker is more inclined to wait for uncertainty to resolve itself or for better conditions in the future. Thus, the additional value that's brought by real options analysis is twofold. Now, about what is long-term investment that we're discussing? The DSO's responsibility as managing entity for distribution networks is the increase of the quality of the delivered electricity to the end users, especially vis-a-vis voltage levels, and to maintain and electrify maintain the network and electrify new clients. To achieve these goals, the DSO invests large sums of money in long-lasting infrastructure yearly, which they look to optimize. Classically, the decision maker proceeds following two steps: technical optimization and economic optimization. During the first step, the DSO looks to optimize the technical behavior of the grid by reducing power losses and outage times and increasing the quality of electricity. In the second step, after having defined the investment that satisfies the technical optimality, the DSO looks to optimize their investment value as well as timing. Currently, as mentioned earlier, the DSO uses discounted cash flows methods to determine the optimality of investment. And to overcome the problems of the absence of representation of uncertainty, we propose to add this real options layer to the economic optimization to complement the discounted cash flow analysis and allow the incorporation of uncertainty. This method has been discussed by Dixit and Pindick in extensively, and we will move forward to discuss the case study to which we applied this method. First of all, we define the case study as a MV-LV feeder, which has already two MV-LV substation, which has already HVMV, substation, which already has two feeders connected to it. We suppose that the DSO has already optimized the grid technically by adding a new feeder, such as shown in this figure here, and this addition helps reduce power losses and reduce the non-distributed energy and power outages. So the DSO looks on the savings made from these reductions as a way to repay the capital expenditures associated with the installations of a new feeder and lines. In this slide, we show the source of uncertainty in our model, which is related to the maximal evolution of the load power yearly. So we take the maximal power on each year, and we have chose this variable because the DSO models their yearly cost based on this variable. So to have a comparative analysis between the existing models and the model we propose, we have chosen this variable. This variable has been, we chose this variable to evolve following increments of a geometric Brownian motion. We have made this choice because it is analytically easier to model this type of stochastic process as a first model, and also due to its similarities with the maximum yearly power variation. To show these similarities, we show the simulated geometric Brownian motion on the left with a deterministic trend line, we can call it, in the middle that shows the deterministic possible evolution. And on the right, we have modeled the data obtained from RTE open data to demonstrate the similarity between both between the behavior of the real load and the models we propose. Also, the geometric Brownian motion allows for the simulation of cases where the evolution of the load might exceed the expectations of evolution, or it might not reach them. The methodology we followed, we start by identifying the economic model, which is relative to the DSO's cost models, and we identify the stochastic variable and propose its model, as we have shown earlier. Then we move to the optimization of the option value, where we add the option value to our cost model and we try to figure out what its value is. And then we determine the optimal investment threshold triggering that investment, and we calculate the option value based after these two calculations. Then we move to analyze our results through a sensitivity analysis on economic and technical parameters. and we compare it with the time continuous results, which are, we compare it with results without uncertainty based on the DSO's model. Now, for the modeling, we have chosen 3 cost models to model the operational expenditure of the DSO. We first start by modeling the power losses cost. I'm going to mention this right now, that all of the everything except the stochastic variable is a constant that we can get from the system's technical parameters and its description. Then we add the cost of not supplied energy. The power losses represent the losses incurred by the circulating current in the power lines. Then we add the cost of not supplied energy, and as the name indicates, it's the energy that is bought but not delivered to the final consumers due to maintenance, grid faults, or other factors. Then the cost of power outages, which is due to the same reasons as the non-distributed energy costs, but it's from the point of view of the power not available to consumers rather than the energy. Developing the expected value yields a second order polynomial in our stochastic variable. Thus, we can write the operational expenditures as we can see here. K designates without reinforcement or with reinforcement to designate the different OPEX, while I designates the feeder for which we are calculating these costs. Of course, it's the sum of all the costs on all the lines. While the operational expenditures depend naturally on the evolution of the maximal power, we consider that the capital expenditures associated with the power lines installation and purchase as independent from that value, and that the installed capacity can accommodate any level of power that might be reached. We have done this the simplification to reduce the amount of constraints we have on the calculations. Of course, it's we are adding it with future models. Then we introduce the option value in the cost model, and we consider that the threshold splits our domain in two. On the left of the threshold, continuation is optimal, and to the right, investment is. So on the left, we continue with our two feeder model, and on the right, we invest in another feeder. K here, we replaced it with WR and R for without reinforcement and with reinforcement, respectively. And given that at the time the DSO is interested in having the largest possible value for the option to invest, and applying the dynamic of the principle of dynamic programming with backward induction, we can write for each very small time step this equation. That states that the option value at time t plus dt should constitute an optimal policy that gives the value at time t. We demonstrate that the equation's solution is a second order partial differential equation and in fpmax, and its solution is of the form a times pmax to the power beta, where beta is equal to this value. Mu is the drift rate, sigma is the variance, and r is the discount rate. After determining the value of the option to invest, we can move to determine the optimal investment threshold by using the value matching condition and the smooth spacing condition. Of course, these conditions have been extensively discussed in literature, and we obtain the value for the optimal threshold to invest and the constant a for the option value. G end, G out, and G losses are respectively the gains on the non-distributed energy, the outage power, and the losses. So they are the reduction in costs for each of these operational expenditures. And the value is given at an annex if you would like to see it. Now, to discuss the results, we can clearly see that the optimal threshold is at 6.75 megawatts as the point of contact between the two curves, representing the gains made from the savings, which is the blue line, and the option value, which is the orange line. This contact point reflects the smooth pasting and the value matching conditions. Furthermore, we look at the differences in the results for the deterministic case or the discounted cash flows analysis and our real options model. We see that by including the option to invest, we have increased our project's net present value by 600,000 euros. We can also see that for an infinite time horizon, the difference between the investment timings isn't enormous, but it constitutes something to further basis for discussion. Then we have added some extensions to our model where we try to overcome the limitations of a geometric Brownian motion by simulating a jump diffusion process. The limitations we are trying to avoid are the inability of the geometric Brownian motion to simulate load jumps that coincide with the connection of large producers or large consumers on the network. To capture this, we have added the jump element dq, which has a value of theta with probability lambda dt and 0 with probability of 1 minus lambda dt. We can also add negative jumps or positive and negative jumps. These are subject for later additions. Redefining this stochastic variable, we proceed in the same fashion as described earlier. And we determined that the investment trigger values for the jump diffusion and geometric Brownian motion are both larger than discounted cash flows analysis, and that the present value when the load is considered as a geometric Brownian motion is the largest of all three, because the geometric Brownian motion incites the decision maker to wait more time, because there is the power is less likely to increase as fast as a jump diffusion process, which decreases the it incites the decision maker to wait longer. As a second extension to our model, we considered that part of the load growth is fueled by the addition of electric vehicles, and a part of these electric vehicles is participating in load shedding and peak shaving contracts. We consider that there is no additional cost incurred by the triggering of this.
Jean-Pierre, you have about 2 minutes.
Yes, I'm almost done. This means that the real drift rate of the stochastic variable is less than we expect. In addition, we assume that the flexibility provided by these vehicles is accessible at all times and is activated directly upon the DSO's request. As I mentioned earlier, there's no additional cost. We have made this assumption to simplify our case study, seeing that our goal is to present the utility of use of real options and the effects of the type of uncertainty on the decision's flexibility. We can deduce from the graph a few things. First, the edges of each area denote the minimum EV integration needed for the DSO to avoid investment. So if we have, for example, if when using a jump diffusion process and for a drift rate of 1.2%, if more than 54% of that drift rate participates in load shedding and peak shaving, the DSO can avoid any investment altogether. Second, the minimum values when using jump diffusion model are higher than those for geometric Brownian motion. In this context, the DSO is more willing to invest in network reinforcement if they expect sudden load jumps than if they don't, meaning that they need more flexibility on the network to avoid investment. Currently, we are working on a cost model that incorporating demand response in the analytical context, and we are going to be looking for similar case studies. So as a conclusion, we complement the existing literature by adding to it a continuous time analytical model, because the existing literature for distribution network investment uses Monte Carlo simulations and discrete binomial lattices, which have their own problems. Of course, we don't say that the analytical result does not have any problems. We propose a dynamic tool that includes uncertainty and reflects decision-making flexibility. And we determine an optimal investment strategy by determining optimal thresholds for the load power and expected investment timing. Thank you for your time, and I hope the subject was interesting for everyone.
Yes, thank you. Thank you, Jean-Pierre. So we can open the floor for discussion. Does anybody have any questions?
It's Reinhard again. I have a question, Jean-Pierre. Very interesting application of real options analysis. And I'm also involved in grid investment studies, but not using real options yet. My question is, can you account for any reactive power needs, or is it just a standard feeder that is invested or not? There are lots of issues when it comes to distribution grids. There are different options that you could think of, like investing in storage instead of an additional feeder. And often it has to do not with only with energy only, but with reactive power, resilience, frequency control, etc.
Yes, there's a mic that's open. Anyway, so yes, honestly, this is the first model we have developed for. I'm sorry, can you mute your mic, please?
Yeah, that's Tatiana Gast. Tatiana Gast, can you mute your mic, please? Maybe the session host can help us here.
Yes,
please.
Thank
you.
Thank you. Okay, so yes, for your question, the framework for the DSO's investment in, for example, in storage units to compensate reactive power is currently very fuzzy in France. I don't know about the rest of Europe. And this is, as a first model, we have chosen a more simpler approach that resembles the approach that the DSO has been making for a very long time, and that specifically targets load uncertainty. So if we want to introduce these additional costs and these additional contracts, it's going to be in a flexibility in a more of a flexibility context, such as demand response, which we are currently looking at. Also, since the conference has been pushed back and we haven't we have added several case studies to this model, but we didn't look at the additional costs that can be incurred by such activities for the DSO. I know it might be interesting, but it just complexifies the whole model, and it was supposed to be as a first step towards the creation of an analytical model for distribution system operators, because it doesn't exist. Again, most of the largest part of the real options of the real options literature in the distribution system framework uses Monte Carlo simulations for investment timing and threshold calculations. I hope I answered your question correctly.
Yes, thanks you.
Thank you. Are there any other questions?
Maybe on my side, thank you, Jean-Pierre. Maybe I didn't notice in the description of the mathematical of the model, but did you consider the possibility of a feedback between the demand for electricity or capacity to your network and the investment by the distributor, the distribution company? I mean, because if the distribution company invests, and by simply investing, it foster demand growth, maybe the assessment of the value to weight changes. Do you consider this effect or not?
Normally, the investment decision of the DSO comes if they think that they might see some constraints appear on the grid. The constraints usually, until now, without the introduction of large DER capacities or electric vehicles or the new flexibility contracts, it's been based on whether or not the load is going to grow or whether or not the equipment has reached deterioration in their physical components. So the DSO's framework is very specific because it treats low voltage consumers, which are residential and office spaces and stuff like that. So it's low power, and there is no such feedback loop where I mean, the DSO will react to an electrification demand where you have a customer that for example, a customer builds a house in a remote area and then asks for the DSO to supply them with electricity. Or in a residential area, you have a building complex that is emptied and torn down, then you have a decrease in consumption. That way, the DSO does not need to invest in larger infrastructure.
So basically, you assume that the dynamics of demand to be independent from the investment decision of the DSO.
Yes, of course. Sorry, of course, if the DSO offers incentives for flexibility, such as demand response, the dynamics will change. And this is what we are currently treating by assuming that there is a cost for incurred by the demand response, and that peak shaving contracts might affect the decision to invest.
Okay, thank you. Now, I'm just asking this because recently I listened to a presentation from Indian DSO, and they are surprised anytime they start to connect areas. They see that when they start to do that, demand for electricity escalates. So actually, they have to invest even more than what they have planned, because when basic connection is provided, the demand for electricity grow even faster, and so they need even to invest more in additional capacity. Thank you.
Of course, in the context of the French distribution network and transmission network, it's already overdeveloped and oversized. So the problem now is how do we include flexibility in our models? How do we react to that flexibility?
Okay, thank you very much. I think we will move on to the next speaker. So thanks again, Jean-Pierre.
Thank you for your talk. Thank you for your questions.
Yes. So next speaker is Benoit Peluchon. So hi again. Please share your screen. Okay. Yeah. So you have 20 minutes, and I will give you a 2-minute warning. So please go ahead, Benoit.
Thank you. Well, good morning, everyone. The subject of this presentation is whether market design for electricity generation has an impact on the cost of capital for generation capacity investment. And as you all know, since the beginning of the century, we had the security of supply concerns expressed with about energy-only markets. And these concerns have grown with the development of variable renewables, has been analyzed by Paul Josko. And these concerns have also increased with the administrative coal phase-out policies decided in many European countries. As a consequence, we saw capacity mechanisms put in place in many countries, such as capacity markets in UK or France, or strategic reserves in Belgium or Germany. And the European Commission position about those capacity mechanisms is, if you remove the price caps, then energy-only markets work fine, besides possible temporary needs for a capacity mechanism, but in the long term, you will not need them if you do what's right. And at the same time, we have seen people arguing that financial risk may be an impediment to capacity investment. So we had RTE, the French TSO, or a consultancy Artelis doing a study for the European Commission, saying that there is too much risk for capacity investment in an energy-only market. But the problem with the studies is that they use risk criteria that are not standard, and especially they did not use the capital asset pricing model, which remains the benchmark for cost of capital discussions. There is also a consensus that renewables have lower cost of capital thanks to feed-in tariffs, as defended by Wind Europe in a position paper. And in the UK, the electricity market reform has explicitly introduced CFDs in order to keep the cost of capital low for low carbon technologies. You have also Newbery and some of his cursors saying that hybrid regulated asset-based model should be introduced for new nuclear, once again, in order to keep the cost of capital low. So the research objective of this work is, can we find some evidence that too high cost of capital, as measured by the capital asset pricing model, prevents enough investment being done, and do the proposed market design lower it? And among those different market designs, which ones are preferable? And as our main results is, yes, the cost of capital is lower with the capacity market, or if you introduce a contract or difference, lower than what it is in an energy-only market design, but this is not true for strategic results. You have one condition for this result, that low demand and the market portfolio, meaning financial markets, have a positive correlation. So the assumption that financial risk prevents enough investment in an energy-only market design without missing money and with perfect competition can be backed by data, and I will show you the result. This implies that it is possible to respect the security of supply criteria and lower cost of generation at the same time if you achieve a lower cost of capital with a change of market design. And another consequence is that if you decarbonize electricity generation, you're bound to see higher cost of capital if you keep an energy-only design. So you may have to introduce some form of long-term contracts in order to prevent such an increase. A few words about the literature. The usual explanation for peak capacity under investment in the presence of a price cap is missing money. There's been papers by Josco and Crumpton and Stoft, which are the initial papers introducing capacity in markets. And you have more recent papers by Lambin and Léautier, or Creti and Fabra, saying that without a price cap and with perfect competition, you either have no problem or you have a welfare degradation if you introduce a capacity market. But some more recent papers, and especially by David Newbery, have been saying that there is another explanation, that is missing markets. Missing markets means that for electricity generation, you only have futures markets for a time horizon lower than 3 to 5 years, meaning that you cannot hedge the future revenues for a power plant because it has a lifetime greater than 20 years. And as we all know, we only get first best results with perfect competition only if markets are complete. So for electricity generation, we have incomplete markets, and some authors, so I mentioned Newbery, but Grubb and Newbery, or some people, Demer, Ehrenman, and Smears, have argued that we need to introduce fixed price contracts in order to to solve this problem, this market failure. So the model, this work is based on previous work that was done with some Toulouse School of Economics researchers, and especially there is a working paper with Thomas Olivier Leautier. And the model is identical to Lambin and Leautier or Cloutier and Fabra, but the only difference is that I have made the cost of capital endogenous by using the capital asset pricing model. Basically, this is a generation capacity expansion model, but with endogenous discount rate. And the idea is to use the CAPM to find what is the appropriate discount rate. It is a static model with one peak technology, but in the paper, you have different technologies, and I will show you results for the whole generation mix. There is no price cap. That means that the wholesale price can reach the value of lost load. So this means there are no missing money, and no fossil fuel prices volatility is taken into account. I assume they are exogenous. And what we are solving is a long-term equilibrium with perfect competition in different market designs. And I will look at the energy-only market, a capacity market with a certain capacity price, energy contracts for difference, and strategic reserves. The setting is that you have one peak technology. All costs are in euro per megawatt hour. This peak technology has a variable cost, capacity cost I, that is expressed in euro per megawatt, then divided by the number of hours in an hour, because we look at one representative year, and the value of lost load is uppercase V. Demand is inelastic and stochastic. We have its probability distribution, and as we are looking at a probability distribution, if the probability of load shedding is alpha, this means that the load shedding duration expectation is simply alpha times the number of hours in a year. And this setting is equivalent to load duration curve on states of nature. So we have stochastic demand, and the question is how to compute the optimal level of capacity given the market design and given the risk given by the CAPM. So investment is decided at time t=0 before load is known, and then production occurs when demand is known. So this means that very simply, the price is either set at the variable cost if load demand is lower than capacity, and if load demand is higher than capacity, then you have to ration demand, and the price is set at the value of lost load uppercase V. If you look at how to express the investment decision, you have to look at the returns for the investment. So if you look at for 1 unit of capacity, you get a gross margin pi equal to a random variable that is simply the difference between the value of lost load and the variable cost times an indicatrix function that depends on whether load demand is greater or lower than installed capacity, and eventually a capacity price. And this is a gross margin expression. This is a random variable, and you just have to divide it by the investment cost to get the random variable that is the return of the investment. And if you take the expectation, you get a very easy expression that is simply the difference between the value of lost load and the variable cost times the probability that load demand is greater than installed capacity divided by the investment cost. And if you link that to the CAPM, we know that you have to compute the beta of expected return to the financial markets returns. So I have written the expression, the usual expression for the CAPM, and I will assume that all the random variables belong to a probability space L2. And I will make one adjustment, is that the CAPM equation can be written in cash flows. And this will help to solve the optimal capacity investment. So if you look at the expression at the bottom of the slide, what we need to find is the covariance between gross margins and the market return eta. This is done through a very simple orthogonal projections onto one subspace of L2. And when you have the expression of the covariance between pi and eta, then you can yield the free anti-equilibrium that is simply given by the equality between investment cost, discounted investment cost, and risk-adjusted expected gross margin. And with this expression, you can find an equilibrium capacity. And this is free anti-equilibrium equation. What you get is a perfect competition equilibrium. The result now, so if we have a positive correlation between load demand and the market, that is eta, the financial markets portfolio, then installed capacity is higher with the capacity market than in an energy-only market. You've got an equilibrium rate of return that is lower too, so you get a lower cost of capital. And for some parameters value, it's possible to get lower total cost with the capacity markets than with an energy-only market. And basically, we've got the same result with the CFD. They are even stronger. For strategic reserve, we do not have the same risk reduction properties, and that is quite interesting. A strategic reserve is a direct procurement of capacity by a TSO to complement what is built by private investors, meaning a TSO has a security of supply criteria. Not enough capacity is being built, so it decides to buy some or install some more capacity in order to respect its criteria. And whenever the reserve capacity is needed, the spot price is set at the value of lost load, even with no curtailment needed. So in that setting, or in that market design, for private investors, there is no risk reduction, but you simply add the cost of reserves to total cost. And if you look at the consequences for the whole generation mix, that is for the other technologies, min-merit and base load, you can see that they also benefit from lower cost of capital with the capacity market or CFD. Always when you've got a positive correlation between load demand and financial market returns, but you've got less risk reduction since capacity price is a lower part of expected revenues. And they have a lower financial risk to begin with. If you look at the merit order, you see that the lower a technology, the lower the rank technology in merit order, the lower its cost of capital. So this also means that when you look at generation capacity expansion models, you should assess the generation technology's relative competitiveness with different discount rates, taking into account the differences in risk premiums. Otherwise, you are implicitly assuming there are cross subsidies between the different technologies. And if you look further, you can see that a decarbonized generation mix will lead to a higher cost of capital because you will only have technologies with low or zero variable cost. And that is what Newberry has argued. This means that fixed costs should be covered by more volatile cash flows, leading to higher cost of capital. So if we get to the results, in order to give you an idea of whether this impact is important or not, I have simply taken 10 years of French hourly load values and used them as a probability distribution of load demand. I've used a CAC 14 as a market index benchmark for the CAPM computations, and the market parameters are set at standard values, such as those given by RWE or E.ON in their annual reports, meaning you've got an equity risk premium of 6%, real risk-free rate of 2%, market portfolio return standard error. And I have used the two values for correlation between load and market return because this can change whether you take 5 years or only 1 year. 1 year may be interesting also because it gives you an idea of the level of risk this can imply for generation capacity investment. And the cost for the OCGTs are very standard. One thing to notice is the value of lost load that is 20,000 euro per megawatt hour, which is in line with the French values used in the security of supply studies. If you look at the results for energy only, as you can see, you've got two tables, one for a correlation value of 0.05 and the other for a correlation value of 0.1. And as you can see, in each case, you have a higher level of load shedding than the French security of supply standard, that is an expected 3 hours of load shedding. And you see that the discount rates for the different technologies are much higher than one is used in usual studies. As you can see, the risk is very high. In fact, for OCGTs, between 13 to 25%. If I look at the capacity market, one thing to have in mind is that I have only assessed the impact of a constant and certain capacity price for the whole lifetime of the peak technology. And the capacity price is set.
You have about 2 minutes, Benoit.
Okay. The capacity price is such that we respect the security of supply. If I look at the results, then I see a clear risk reduction for peak capacity, and I'll also get an expected price decrease by comparison with energy only. If I look at the contract for difference, just one thing to notice is that it's 15 years energy CFD. Then I get even lower cost of capital at equilibrium and lower expected price for consumers. And you can notice that the CFD does not suppress all the risk. One point is that a lower cost of capital can be welfare improving, and that is something that is not studied in itself in the work, but for that you would have to discount the social discount rate. And some of the papers have done it, but it is a normative approach. You have to use a utility function for representative agents. And as you can see, apparently those studies give a much lower social discount rate, meaning that lowering the cost of capital through a change of market design seems to be a welfare improving measure, as it allows more investment and it allows capacity investment to be more in line with the first best outcome. So the conclusions, and first thing is that financial risk do indeed seems to be an issue for generation capacity investment in energy-only markets, even in the absence of price caps or market power. The market failure is missing markets. Obviously, you have a problem with peak capacity, but the problem, you will have the same kind of problems in decarbonized electricity systems because you will have more volatile cash flows. So this means that some form of long-term price signals will complement the short-term wholesale markets, what is so-called hybrid designs, may help solving this problem by lowering the financial risk for investment. And this market design.
Benoit, I think
yes,
that maybe we can just pause there and see if people have questions, and you can use their responses to the questions to make your final statement.
Okay.
Is that okay?
No problem.
Great. So thank you. Are there any questions?
Maybe if I may, Benoit, thank you for your presentation. So basically, you show that with capacity mechanism, you can reduce the cost of financing generation assets, right? But implicitly, it seems to assume that you are able to have, let's say, perfect capacity mechanism, because this probably is the limitation of this exercise. You show that energy-only markets. Okay, so we agree. This was my question, because again, there is how much capacity do we need, and this is also a source of uncertainty for the policymakers.
Yeah, basically, I have assumed that we know which security of supply standard you want to respect. And I know this is a debate at the European level.
But it's interesting anyway, because it reminds me the article of Josco a few years ago, showing that LCOE is not the good metric, because also the value of generation is not the same for all generation technologies. Now you owe to that also the cost of capital you show should not be considered the same for all generation technologies. And so you provide more nuances on how to better assess, let's say, the best generation mix, let's say.
Yeah, definitely. I think even if you do not agree with the results for capacity mechanisms, one thing that's important is that the competitiveness of the different technologies should be assessed with their own level of risk. And so you should use different discount rates. And one interesting feature of this work is that it gives you one method to do that in the context, very classical context of generation capacity expansion models. And one thing interesting too, I think, is that it gives some credence to what Newbery has said or what has been done in the UK in the context of the electricity market reform. And I should add that there are some extensions I'm working on in the context of decarbonization in order to show that, yes, in a decarbonized generation mix, you will have higher cost of capital than today if you stay in an energy-only model.
Great. Thank you very much, Benoit. Any other questions? Okay, well, then thank you, Benoit, and thank you, Nicolo, for the question. So we can move on to the final speaker. That's Reinhard Madlener. So Reinhard, please share your screen. Great. And yeah, you have 20 minutes. I'll give you a 2-minute warning. So please go ahead.
I'll make it big screen, but it takes a few seconds. Sorry about this. And I can start talking in the meantime, I think.
Yeah, just if you're open.
Now you should see it. So good morning, everybody. It's nice to be together, not in Paris, but at least digitally, and gives me an opportunity to present this work that we started quite some time ago. The history is that I got interested in portfolio optimization for power generation assets about 15 years ago. It was the time when I met Shimon Auerbach, and yeah, he told me about his work, and then sadly a few years later he crashed in a plane accident. And in 2007 I went to Aachen University and met Professor Zimmermann, one of the big figures of fuzzy set theory. So bringing the two together, we found an interest in looking into the application of fuzzy portfolio optimization applied to power generation assets. And this is a follow-up study that where we focused on onshore wind power plants only. There's quite a bit of research that has linkages to this work. For example, we are currently looking into spatial diversification from a system cost perspective. We have done some work on the spatial portfolio optimization with mean variance portfolio analysis for cogeneration and for wind. There is a study on regional auctioning that we're currently writing on for Germany, onshore wind as well. And so all these are somehow related to each other and give us different perspectives about how and when and whether and where to invest in power generation like wind. So my co-author is Barbara Glensk. She likes to do the programming, and here is the overview. I'll start with some basic motivation, our research questions, then I go to the methodology, introduce you to the case study and present the results that we got, and then I will conclude. Here is the chronology that I already mentioned to Markus. So it started actually in the 1970s with Barlev and Katz, and they did one of the first studies ever using portfolio optimization in the context of fossil fuel mixes for US power generation. Then we had Auerbach and Berger. That paper was already cited by Markus in his first presentation. And they were, I think, the first ones to use mean variance portfolio analysis in the context of European liberalized power markets. And then there were a bunch of papers where I was directly involved, Krei and Zweifel, two of my close colleagues at ETH Zurich and University of Zurich. We did a study, Christoph Wenck and I, in 2008, looking at peak and off-peak power generation for the case of Switzerland. Basilian did a study with Fabian Roques and so forth. So it's a list of articles that try to make use of this standard mean variance portfolio analysis a la Markowitz. And then we went on and looked also into fuzzy set theory. You see in between those marked with a star, early studies on the use of fuzzy set theory for portfolio optimization. That literature is still kind of scarce. So the optimization is important when investors need to know what is my optimal portfolio, and we could also discuss whether this financial viewpoint is a good one in light of real assets with technical constraints and so on, but that's not my main focus here. When we look at wind parks, we have different technologies, we have different sizes, we have different ages of those wind turbines that can be used. So weather conditions play an important role for the profitability, which is why location matters. And then it comes to asymmetric versus symmetric risk measures. The standard mean variance portfolio analysis uses as a risk measure the variance, which is a symmetric risk measure. But Markowitz himself in the late 1950s pointed out this is actually not what investors are concerned with. They are happy if they have the upside risk, i.e. make more profit than expected, and they only are concerned about the downside risk. So why not use a one-sided risk measure? And this is exactly what the semi-variance is, or the semi-mean average deviation. MAD, SMAD, semi-mean average deviation. And that is the risk measure that we decided to use in our study. Fuzzy set theory, some of you might be familiar with it, but this is in a sense more flexible as you leave the probabilistic world and you accept some vagueness, some fuzziness in terms of the subjectivity of the investors' perceptions and preferences, and also the knowledge that is being involved. So fuzzy set theory as an alternative that can be used, and then it's interesting to see what different results you get. And we also did some studies in a more general setup, for example, where we used all different kinds of generation technologies and different types of methods, and then we compare the results with each other. So here we are more focused in that we restrict ourselves to onshore wind only, and essentially the semi-mean absolute deviation approach. Now, regulatory changes also gave us a headache, because when we put this paper aside, it's a working paper that is available online, but we put it aside some years ago and realized that the Renewable Energy Act in Germany was faster than we were, in the sense that it was amended several times. Originally, we used the EEG, the Renewable Energy Act, EEG 2009 regulation for our analysis. And then there was an amendment in 2012, 2014, 2017, and I think 2021 was the latest. Here are the research questions. We want to investigate how can different onshore wind parks be combined to come up with an efficient portfolio, in the sense of either you want a possible expected return on your investment for a given risk level, or some desired expected return for a minimum risk. We want to show how useful is the application of fuzzy set theory for wind farm power portfolio selection using our semi or asymmetric risk measure as a risk measure. And thirdly, we looked into the impact of different regulations for promoting renewables in Germany and what impact it has on the results. Now, as I said, there are related studies here. You see a few references of our own work. And then we also had a project where we looked into whether to use the net present value as a measure of profitability, or whether you want to look into something like the annualized return. The annualized return seems to be more useful when you have existing power plants rather than an investment in new technology. Because it tends to be difficult if you have existing long-lived power plants to get even the historical data for those if the investment took place 10, 20, 30 years ago. Now, the maximal share for each technology might be a technical restriction that needs to be considered, and in that early works that I mentioned in my previous slide by Wenck and myself, or Zweifel and Cry, we already looked into such limitations on capacity addition that are maximum possible or that make only sense in a portfolio. And when you look at a country study, that's not what we look here, but all power generation technologies in a country setup, then you might want to limit the individual shares of the individual technologies, because it does not make any sense to have 100% wind power portfolio. That would not be feasible, technically speaking. So we apply Zimmermann's 1978 fuzzy sets method, and that involves the calculation also of sufficiency and necessity levels for the risk and return needed for specifying so-called midpoints. This is the problem that we look at. Capital lambda is the one that we want to maximize. This is a logarithmic transformation of a lowercase lambda divided by 1 minus lowercase lambda, and lambda, the lowercase, is the value of the membership function. There are several alphas involved that determine the shape of the membership function, which, by the way, takes a logistic or S-shaped shape. And then we have some R and W's. R refers to the expected returns, the W to the risk involved. And so we need to determine also this RM and WM that you can see in those equations. And they are related to this necessity and sufficiency values. It's the average of those two, and that allows to calculate these RMs and WMs. And then we have the RIT, that's the expected return of a specific asset I in time t. All assets have shares, and all the shares together need to sum up to 100% or 1. Lambda needs to be non-negative, D needs to be non-negative, and lowercase d refers to the deviation in the return from the expected return. That's also one of those constraints that you can see on this slide. This specification goes back to Wattada, 1997, the first one specifying such a fuzzy semi-mean absolute deviation portfolio selection model, not in the context of energy. I think we are the first ones who are doing this in the energy context. And another work that was by Fang et al. In 2008 also refined the Wattada specification. Now the steps are here. We determine the net present value for each individual wind park using Monte Carlo simulation and the crystal ball software based on technical and economic data. I'll show you an overview of that in a moment. Step 2 is to specify the sufficiency and necessity levels for the return and risk. obviously this would need the involvement of the decision makers, of the experts, to shape those parameters and eventually the membership function. We just did this in an illustrative way, but in practice you would need to involve the stakeholders. And step 3 involves the determination of efficient portfolios and the frontiers for the fuzzy semi-mean absolute deviation model. One advantage of this approach, by the way, is that you can apply linear in contrast to quadratic programming. So it also simplifies the computational effort compared to the Markowitz mean variance approach. Now here you see some summary of the wind turbines that were involved and the federal states. You can see we have 5 wind parks, one in Saarland, one in North Rhine-Westphalia, one in Lower Saxony, one Saxony-Anhalt, and final one in Hesse. And you can see the number of turbines varied. This gives up a total capacity that varies, and also the year of the putting into operation varied. Then you see the EEG regimes and how the remuneration changed over the years. You can see that the initial remuneration went down from some 9.2 cents per kilowatt hour to 8.38, and the base remuneration from 5 to 4.66. Now, the complications of this German regime, I'm not discussing a lot, but it has to do with some so-called reference yield, and that the operators of a wind park get some higher remuneration for a limited number of periods or years, and then it goes down to some other, this called base remuneration later on. It depends on the wind site conditions at specific locations. It has been changed over the years again. Now, here's some technical characteristics. You can look for yourself some diameter figures or the number of blades. That's all the same, material same, but in terms of the power limitation, they vary. Nacelle height and what we expect as reference yield varies. Economic characteristics on this slide, where you can see some technical life, remaining lifetime, and so forth. All that is important to calculate the net present value and do the cash flow simulations. In terms of results, first I show you a comparison between the regime that we had in 2009 and the one in 2017 and the ones in between. And from the graph, you can see that there was a minor change switching regime from EEG 2009, here on the right upper corner, to EEG 2012, which means you have a slightly lower expected NPV on the y-axis for about the same risk situation. That's the regime change from one amendment of the EEG to the previous one. But there is apparently a big change to the EEG 2014 in the sense that there is a substantially lowered NPV for these portfolios that are on this little efficiency frontier, and a lower risk as well. And moving further, we have an even lower risk and a lower NPV for the EEG 2017 regime. And this is just looking at feed-in tariffs and how they imply on the optimal portfolios that we get. On the next slide, you see a comparison between the frontiers that we get under these different regimes, and now looking also into the market premium regime. This has to do with some spot price development valued over a period of a month. And then this is like a breathing markup on what operators of wind parks get. And you can see this is quite distinct in the sense that it is a lower NPV or expected NPV compared to the early regimes, but a higher one compared to the later regimes, and in any case, a much higher risk that those operators or investors need to take. And then we can look at the comparison between EEG 2017 using the feed-in tariff on the lower left-hand side of this graph versus the market premium model on this upper right-hand corner. And you can see that the efficient portfolios do have a higher risk in compared to the efficient portfolios that you would get feed-in tariff regime, and efficient portfolios have also higher returns in comparison to efficient portfolios obtained for the feed-in tariff regime. So it's risk and return that is affected strongly, switching from the feed-in tariff to the market premium regime within the same Renewable Energy Act 2017. Now, next I show you some tables, and here you can see the portfolio structure. And from that, we learned that apparently of the 5 wind parks that we looked at, wind parks 1, 2, and 5 are irrelevant. And for the optimal portfolio combination, only wind parks 3 and 4 matter. And wind park 4 apparently seems to be the most attractive or dominant one, with a share of 91% versus about 9% in this portfolio P1. On the efficient frontier, you can see where P1 is compared to P10 and P11. So these are different combinations of wind turbines at different locations, giving the efficient frontier. And you can also compare this efficient frontier with the individual wind parks, 1 to 5. And you can see that these are apparently doing worse in the sense of that they have a lower expected return and a higher risk. So these are certainly not close to the efficient frontier. And also wind park 5 can be explained that this is dominated by wind parks 3 and 4. If you look at 3, this has a low risk or lower risk than wind park 5. And wind park 5 has a higher NPV than wind park 3, but overall it turns out that wind park 5 is not attractive to contribute to neither a higher expected return nor lowering the risk. It doesn't really help.
Reinhard, you have about 2 minutes.
Yeah, thanks. And on the right-hand side, you see the comparison with the EEG regime 2012 compared to 2009. On the next one, we can compare EEG 2014 with 2017 and so forth. And for the market premium model, you can see that this efficient frontier is again very far to the right. So there's much higher risk involved, but also the chance for higher returns. Using this alternative risk measure, such as this SMAD, simplifies the calculation. That's one interesting feature, and better reflects investor real losses. In combination with fuzzy portfolio selection models, it allows to develop a new perspective on power generation selection problems. I showed you that feed-in tariff support schemes have a negative impact on the investor's possible return. Changes the type of the support scheme also has quite some impact on these returns, but feed-in tariffs tend to have lower risk. And well-diversified portfolios, such as the ones you would obtain with classic mean variance approaches, as well as the alternative ones, can be set to be used for such kind of decision making. To conclude, how should different onshore wind parks be combined? Well, showing our analysis, we find that the efficient portfolios obtained consist at maximum of 2 wind parks only out of the 5 we looked at, irrespective of the regime. Efficient portfolios with the highest return always consist of wind parks 4, which is the biggest one, and 1 of 2 installed in 2007, which were the youngest ones we looked at. And how useful is fuzzy theory for portfolio selection? Well, we showed this as a promising approach where investor risk and return expectations can be incorporated into the model, positively affecting the decision maker's problem in the sense of a smaller set of decision alternatives to be considered. And thirdly, what's the impact of regulatory change? Well, the changes in the regulated promotion scheme have a significant impact on the portfolio characteristics, but less so on the portfolio structure. Finally, regulatory change, especially the EEG 2017 amendment, brings new opportunities for business decisions regarding the form of participation in the energy market. Thank you for your attention. I'm open to any
Thank you. Thanks, Reinhard. So yeah, we have time for a question. Anybody is interested?
Yes, if I may.
Go ahead.
Thank you very much for the presentation. So I did not 100% get about technology shares of the portfolio, basically. So these 5 wind parks, are these the 5 biggest ones in Germany?
No, not at all. The select, we just got a data set. We tried to collect data on specific wind parks, and that's what we found.
And what's the intuition that 3 of those 5 are not in the optimal portfolio? Are they just too old of a technology?
Yeah, that could be one reason. I mean, it's kind of an arbitrary selection of turbines. And what we thought of is, why not look at the 5 locations using each technology? This is technology and location together as pairs. And that's just the setup we have. And we look at, does this make an efficient portfolio, and what are the individual shares of the technologies? And we find that 3 out of 5 are apparently not useful for an efficient portfolio. You like to mix 3 and 4, and 4 dominates, which would lead to the question, well, how can you achieve a 90% portfolio share of wind park 4 and the 9% portfolio share of wind park 3? So what we could imagine is that you want to build 9 or 8 or 9 additional wind parks 4 in Saxony-Anhalt. That's the only interpretation that I can come up with to make this analysis useful in practice. And then, of course, that raises the question, are there still sites available where you could realize these? And as I said, you could also combine all the other technologies with all the other locations, and then you get a lot more results to check whether some technologies could be more useful at another location than the location that we studied.
Yeah, this would have been a question, how the technology shares can actually also be interpreted then. Okay, thank you.
The other thing that we look at, by the way, is about the remaining lifetime. You know, if you decide to invest in an existing wind park with the remaining lifetime, that also raises issues like repowering investment decisions. We did some research on using real options analysis on the topic of repowering to find out whether it makes sense to invest in an already used wind park, not a new investment, greenfield investment, but to buy an existing one with some small remaining lifetime, and then you need to know what is your repowering option.
Thank you very much. I think because now it's 11 o'clock, we'll have to end the session here, but I'd like to thank the 4 speakers, Markus, Jean-Pierre, Benoit, and Reinhard, for their talks, and to everybody else for your interest and your follow-up questions. I'm sure you can contact the speakers directly or meet in one of these breakout rooms if you wish. So I don't know how those work, but there are plenty of them this afternoon and tomorrow to try them out. Otherwise, see you virtually and maybe even in person next year. So have a nice rest of the day and conference. So thank you, everybody.
All right. Thank you, everyone, for joining this session.
Thanks to all.
I hope you have had a very nice time in this session this morning. So, and I hope you also enjoy the rest of